All right, so now we're going to move from one dimension to two dimensions, and we're going to look at vector positions and displacements. Basically, what we're going to do is we're going to say, previously we did everything along a line, right? The positions were on a line. Now we care about where in space things are. So to look at that, I mean, we're looking at something that's more or less like a map of the room or the experiment or the ocean or whatever it is we're looking at. We're looking at a map or a chart or something. But remember, when we were talking about the position, we were saying that the position was a mathematical representation of its location. So, I mean, that sometimes gets people screwed up, right? People start thinking that the position and the location are the same thing. But in the real world, there's no real coordinate system. But in physics and math, you have to sort of assign numbers to things. And you assign numbers to things in two dimensions, sort of the way you do it in one dimension. You just assign two numbers to it. So the position is an ordered pair. We usually call it x and y. That relate that express the coordinates. Of the position. Again, this is like a map or a chart. So we're going to look at just sort of the coordinates of something like that. So if we had a position here, we could have a vector A here. That is the position vector for this spot A. Okay. And that position vector would have some expression, right? It would be like 1 meter to the right, comma, 2 meters up, right? X first, Y later. So that's our initial position, A. Then we might have another position way over here, C, and that would have some sort of expression as an ordered pair. A second kind of thing we might look at is the displacement. This is a very similar idea as the position. It's the location or the position of one point relative to another. Okay. And it represents the straight line between them. Okay, that means that it represents a trip, basically. If you take a trip from A to C, you have to travel there through the displacement vector b, which also has some expression. Here we'll say 6 meters, 3 meters. Okay. So the displacement is similar to the position, only the displacement is in a random position, right? You can say my displacement starts at A and goes to C, whereas all positions start here at the origin at 0, 0. So all positions are like displacements from the origin, displacements from the place we choose to measure from. Remember we said the origin is completely arbitrary. We just need to agree on it, and once we've agreed on it, then we can start saying this is so far east and so far north of this origin. It's just wherever we decide to call 0. That's just our thing. Wherever we decide to call 0, that's our origin. Right? So, we had our C over here, so B would be from here to here. That's 6 meters, 3 meters. Okay. And finally, we'd want to find C here. Well, finding C is like taking a trip is from the origin to this point C. It's going to be this vector here. But that's also like taking a trip from the origin to A, then taking a trip from A to B. So the way we do that is we say 2 consecutive trips position is the sum of each trip's displacements. Okay, so A to C is equal to A to B plus B to C. Okay, or something like that. So we'd end up here with C is equal to A plus B here. A plus B equals C. A is 1 meter, 2 meters. B is 6 meters, 3 meters. And so when we add, we just add components. So if we went 1 meter east and 6 meters east, 1 meters east first and then 6 meters east second, we went 7 total meters east. We went 2 meters north, then 3 meters north, we went 5 meters total north. Okay, so it would be 7, 5. All right, and that's more or less how this works. And I should have used different letters. So what we just saw here is we had 2 very similar ideas. One is a position and one is a displacement. A displacement is a trip on a map. It's all on a map because we've added coordinates. So the displacement represents a trip on a map, just as the position represents the location of a place or a thing on a map, right? And so that's basically all we're doing is we're trying to think of these as they are on maps, right? We're just adding 2 things together. 2 displacements make a third displacement, right? We start at the origin, do A, do B. We end up the same as if we'd had done C. So that's another displacement. And we add these things together. And this displacement has to be less than the distance here has to be less than the distance traveled by each of these displacements. But it's fairly straightforward. So when we're actually just adding these things, it happens right away. I'll do an example. I'll do one example the whole way through here, dealing with, I don't remember exactly what it's dealing with, but it has to do with positions and velocities and stuff like that. But first we'll find a couple of displacements, a couple of positions and a couple of displacements, and then we'll go through, talk about velocities and stuff like that. Then we'll calculate the average velocity. Then we'll talk about magnitudes and directions, and then and from that we'll find the average speed, or the speed and the course of a ship. All right. So that's what we're going to do for the rest of this time. Thank you very much. I'll talk to you again in just a minute.